welcome back. In the last class we were working on the Legendre transformation in order to obtain the thermodynamic functions where the natural variables are something which you would like to control, such as T and pressure and volume and so forth. So, we have developed two expressions, one for Helmholtz free energy, okay, where the natural variables is dV n's, and the other one is basically the enthalpy, where the natural variable is Sp and n's. Okay. Now, we will be extending this exercise for the case where essentially we would like to change Sv n1 to something like Tp n1, so forth. Okay. So, what would be the function appropriate for that? So, in this case we have two variables which we are trying to change. So, in a sense this multivariable. So, that means that we have to worry about two specific slopes. The first one is del u by del s at constant v and I. So, this, if you look at the thermodynamic relation in the differential form for the internal energy, it is T ds minus P dV plus summation mu I dn I. So, essentially del u by del s is nothing but T. So, that is one of the slope, and the other one is going to be del u by del v s and this is nothing but minus P. So, we have two specific slope which is available. Now, in order to obtain the Legendre transformation function, we are going to use u minus the first slope, okay, del u by del s multiplied by the variable which we would like to change, which is s, minus the second slope multiplied by the variable which is v. Okay. So, this is the Legendre transformation phi. So, this is going to be u minus T s minus of minus P v, okay, and that is u minus T s plus P v, and this particular function is often called G. So, G is nothing but the Gibbs potential or Gibbs free energy we call it. Now, G is a function of Tp n1 till n t. Okay. So, if you can take the derivative of this here, that is going to be dG is equal to du minus Tds minus sdt plus Pdv plus Vdp. Okay. So, you can use this, expand this or replace this by its own expression Tds minus Vdp plus summation mu I dni. Now, you have this which comes here minus Tds minus sdt plus Pdv plus Vdp. Okay. So, this cancels, okay, and this also gets cancelled. So, what you have is Vdp minus sdt plus summation mu I dni. Okay. So, this is our expression for dg, and the independent variables are p, t and ni. Okay. So, you may also like to test whether we are going to get the original expression if you do inverse. So, let us do that. So, we have to get back the g, that means from g Tp n1 till nt to u s v n1 till nt. Okay. So, this is the transformation we would like to have it, and check whether we are going to get back u or not if we this change t and p to s and v. So, here again you do the similar exercise, g minus the variable which you would like to replace. That means, you have to take the slope with respect to that, p is constant and ni's are constant, and then multiply by t minus, okay, you would like to replace this keeping t and others constant, and here is p. So, if you look at this differential expression, then this is nothing but minus of s, and this is nothing but v. So, you have now g plus st minus v times p, and now let us look at what is this expression, because by definition we were G was u minus Ts plus Pv. Now, if you look at it there, then if you bring this Ts and Pv to the left hand side, this must be then, this is nothing but u. Okay. So, we get back the original function, okay, by doing this inverse approach. Okay. So, you can also consider not just this two variable, but you can also try to get h, because h is nothing a function of s and p, right. H is a function of s p. So, essentially you can also replace or you can also transform s to t, or take the s to the is partial derivative, or that means slope, and you can get the same expression as g. So, let me try that and show this demonstrate that part. So, what I am trying to say here is that we can also try this h okay, to t p n 1 and t, and this is a function g, okay, which means we are talking about g is equal to nothing but h minus del h by del s, or rather I would say some function, let us say, which should be same as g. Okay. So, this could be your phi again, this h minus del h by del s at constant p n i's, and this is h. So, if you look at the differentiation or the derivative expression or expression of h in the differential form, it is dh here. So, the derivative of this with respect to s, keeping the rest constant, is nothing but t. So, essentially we have this as t. Okay. So, you have h minus T s. Okay. So, but h is nothing but u plus P v T s, and this expression is nothing but the same as the earlier expression when we calculate the function g. Okay. So, if you look at the function g, it was u plus P v minus T s, which is nothing but h minus T s. Okay. So, this is the same expression which we obtained here. So, this is nothing but g. So, you can consider by changing sequentially all these variables, or you can consider all the variables to be changed by these derivatives. That is also feasible in this mechanism. Okay. So, similarly I can also consider a is t and v n 1 and t. I can get a function t p n 1 and n t. Okay. So, if you do this exercise, you will get a minus del of a by del v, keeping t and n constant, and this, if you look at the derivation of a, then this is nothing but the derivative, partial derivative of a with respect to v is nothing but minus p. Okay. So, a plus p v, okay, is the function, and a is nothing but u minus T s plus P v. So, this is nothing but g also. So, essentially you get the same expression. So, if you recall your Euler equation, this is an interesting aspect here. It was u is equal to T s minus P v plus summation mu I n and I, using the extensivity of the thermodynamic function. So, we obtained this relation, if you recall. Now, you can extend this relation to the different thermodynamic function which we just derived. So, we can demonstrate this for Gibbs free energy. So, if you look at the Gibbs free energy definition, u minus T s plus P v is, if you take this here, rearrange this expression, is going to be mu I n I. So, this is nothing but g. So, g is nothing but summation mu I n I. So, this comes directly from the Euler relation. Okay. Now, as of now, we just looked into two intensive variable t and p. Okay. We converted S to t and volume to p, but now we can think of another intensive variable which is chemical potential mu. So, which you would like to convert the conjugate variable n to its to mu, which essentially can be done in the same way that we can demonstrate. And let us do this, consider S v n and a corresponding thermodynamic function which is u, and what we want to do is we want to convert this let us say only T, and this we can do that mu, okay, for, and we are considering only the single pure systems. Okay. So, if you want to now convert this S to T, let us say N to mu and as well as V to P, then we need to come up with the derivative of U with respect to S, and let us consider that we are interested only in the pure system. This S minus del U by del V, S n and constant multiplied by V minus del U by del N S V constant multiplied by N. So, this is nothing but chemical potential, this is nothing but minus of P, and this is nothing but T. So, you have now a function U minus T S plus P V minus mu n. Okay. If it is a multi-component system, then we are going to have mu I, n I, and there is going to be summation. Okay. So, now if you look at the Euler equation which we have written earlier, the Euler equation which is written there was U is equal to T S minus P V plus summation mu I n I. So, this clearly means that this function is nothing but 0. Okay. And this is sometimes we call grand canonical potential, which is nothing but a function T P mu I mu R. Okay. So, from this expression is basically the Euler expression which we come up with, and this expression yields the value 0. Okay. Now, in the later part what I am going to show is that if you have a system, so this is a type of system. So, this if it is S V n, we have calculated the function or potential, okay, thermodynamic function. The corresponding natural variable is U, which we are now aware of. The corresponding T V n natural variable is A natural function is phi. That means, for A natural variables are T V n. For the case of S P n, the thermodynamic function, appropriate thermodynamic function is Helmholtz free energy. For the case of T P n, the appropriate function is G. So, that means, for U natural variables are S V n, for A natural variable are T V n, for H natural variables are S P n, for G is T P n. Now, in the earlier in the early stage of this course, we described that for equilibrium we looked into the maximum entropy. In the later part, we are going to show that equilibrium can be also shown by considering the minimum A, H minimum, okay, and G minimum. So, these are the minimization of this thermodynamic function would also attain the equilibrium conditions, but for the corresponding natural variables. For the case of S V n, okay, we had either S maximum, okay, and later on we are going to show that S maximum or U minimum are equivalent, okay, for the case of equilibrium conditions. Okay. So, the other set of Legendre transformation we are not going to show. Those are those cases for which we are using the S as a function for basically U V n. So, the basis we have considered is basically the internal energy as a function, and we were trying to transform the variables in our interested variables such as T P. Similarly, you could do the same thing for S, okay, and you may get another function. Those functions are sometimes called massive function. Okay. So, we are not going to deal with those functions because this is something which we are interested. So, let us say U is a function of U S V n, okay, and du is equal to T d s minus P d v plus mu du n. So, here I am just taking the pure system. A, or sometimes it is also called F, is a function of T v n. So, dA is minus S dt minus P d v plus mu dn. Similarly, you have S p n, so that is H. So, dH is T ds plus V dP plus mu dn, and then finally, the G, which is a function of T p n, and here is minus S dt plus V dP plus mu dn. Okay. So, this summarizes basically all aspect of the new thermodynamic functions which we have developed for different intensive variables or the changes in the variables which we are interested in. So, these are the 4 generic expressions which we are going to make use of it in the later part of the course. So, that is something which I wanted to cover this class. In the next class, we will be looking at some further expressions or derivations particularly which is relevant in order to get the thermodynamic functions in the real conditions and that we call it Maxwell relation. Okay, so, I will see you in the next class.